Okay, hi everyone. Good morning. Welcome to the next week of our course. Um, so, is everyone able to uh, hear me? I hope so.
Yeah.
Okay, great. So, are there any questions before we begin on on course material? I will be very happy to discuss anything, any issues before we move on. So, okay. Um, So today I want to discuss, so here's the agenda I have for today's discussion. And we're going to finish our introductory discussion of work. And then we'll move on to heat interactions, which is the second major abstract way that systems interact with their surroundings. And once we discuss heat and work, we will be able to address the first law of thermodynamics, which you've all heard about. And this addresses the conservation of energy. And so once we define work and heat, we will naturally, when we discuss Joule's experiments, come to something that's called energy. And at this point, we really will, I hope that you'll see that's something very, it's very neat in the sense that it comes out of nowhere. It's kind of cool to have this approach to see what energy is. And then finally, I hope to get into something called a reversible process. This is a very important process. You may have heard about this. You may have heard the term reversible when it comes to chemical reactions. This is the same word again, reversible, but we're going to apply it in the context of optimum work, and then look at the implications of this scenario and this type of process called a reversible process. Okay, so that's the agenda for today. And so I'm going to move on. And just to recap, really about this introductory discussion of work, we saw that work for this course, dW is in the most general sense minus P external times dV. And so we will be looking at, as we develop the theoretical framework for a lot of the thermodynamic words that you've come across, we'll be looking at pressure volume work. Okay, and that's very obvious from this definition of work, since pressure and volume are involved. And we know that PV has units of energy, because just if you look at the dimensional analysis of the ideal gas equation of state, this is the ideal gas equation of state, so I won't call this the ideal gas law anymore. We'll call things equations of state now, and equations of state relate pressure, volume, and temperature. And we see that R has units of energy per mole per temperature. And so that's one set of units. You can also have R in terms of pressure times, you can have it in terms of bar liters or liter atmospheres per mole degree Kelvin. So these are typical liter atmospheres per mole Kelvin. That's one unit, one set of units for R. Another one is just energy. It could be joules per mole times Kelvin. And so you see here that if we multiply R times N, which is moles, and T, which is in Kelvin, we get joules. And so we see that PV, this combination of pressure and volume, is really just an energy unit, actually. So it's kind of interesting that, if you look at dimensional units, really give you a lot of insight into some things. And if you never really thought about it or took time to think about it, PV is energy, okay? It's not just liter atmospheres or whatever units of volume you want times pressure. It's actually energy. So we see then that work, when we multiply it by pressure and volume, because this is really what we're doing, here's pressure. This is just some amount of volume change. So this pressure times volume has to give us something that's energy. And of course, joules is energy, and joules is something that we know is associated with work. Okay, so we know that this is work. We also know that work, And please chime in. Just unmute yourself and chime in if you need to ask a question or if you would like to contribute anything as well. Your contributions are welcome. Okay, it doesn't necessarily have to be a question. It can be a comment. So work is a state function. And by that, what I mean is that it's path dependent. Okay, and we saw this with our analysis of work on a pressure volume diagram. We saw that if we have a cycle where we start from state 1, 2, 3, 4, so we go around in a cycle, we analyze two processes, one where we go from 1 to 2 to 3, and the other one where we go from 1 to 4 to 3. So we see in both cases that the final and initial states are the same, 1 and 3. The intermediate state is different. In one case 2, the other case 4, and we saw that the two works, the amount of work for each process was different. So work total for process 1, 2, 3 does not equal work for 1, 4, 3. Okay, and this was very important, and that goes to the fact that work is path dependent. It depends on the path you take between two distinct equilibrium states. And of course, the way we set up our argument here or our discussion, 1 and 3 are distinct equilibrium states. And in fact, 2 and 4 do not have to be intermediate equilibrium states. You can have a process that ends up in equilibrium states at the ends, but it could go through some states which are non-equilibrium. That's fine, but that's any kind of process. Okay. Finally, we also know that for a cycle, and this is what a cycle looks like, as an example, right? You start at some point and you come back to that point, 1, 2, 3, 4. For a cyclic process, W total for the cycle is not necessarily equal to 0. And this is something that you really want to be very careful of, okay? Never, if you're given a cyclic process, never presume that the total work for that cycle is 0. Okay, make sure you calculate the work, or if you don't have numbers, at least make sure in terms of the variables of the problem, you can convince the person who's asking the question and yourself that the total work is or is not 0. You could have an anomaly where it is, but this is not necessarily 0. So keep that in mind. Okay, any questions on that? Okay, awesome. So we saw that work, and here I just want to digress, a very quick digression here. We saw that work is path dependent, sorry, okay? It depends on the process and the path you take. I want to consider things or properties, so let's consider system properties or functions. Or functions that are path independent. And I'm going to ask you all, the captive audience here, what you might think are some system properties. And in this course, you can take system properties as functions. And we already saw this through the equation of state. A system property such as pressure, that's a property of a system. Temperature, which is a property of a system, can also be considered a function, because the equation of state, whatever that is a function that relates temperature, pressure, volume, and we'll put n here as well, okay? So the equation of state is some function. That's what F represents here. It's a function. And in fact, formally, it's some function that is equal to 0. And so this is a very general definition of equation of state. And so we see here that if we have a function, it can be written in terms of variables, in this case, system properties listed here, okay? And in fact, just going to our handy ideal gas equation of state, we see here that if I bring the nRT to the other side, we indeed see that this function of pressure, temperature, volume, and n is equal to 0. And that function of pressure, temperature, volume, and n is just PV minus nRT. but that's still equal to 0. And so in this very simple equation of state, we can see what the general form of what an equation of state is representing. Some function of these system properties or variables that is equal to 0, okay? And so if we use our equation of state, we can actually write pressure now as nRT. Again, this is the ideal gas. It's very simple, so we can write it down very quickly. But we see here now that pressure becomes a function of temperature, volume, and N. And we don't write R because that's just a constant. So you see here that the system property pressure can actually be written as a function. That's why in this discussion point here, I say that let's consider system properties or functions that are path independent. Okay, so system properties can be functions, okay, or variables. They can be anything you wish them to be. And if you always keep in mind this relationship for equations of state, you'll see why you can interchange these things. Okay, so can anyone? So now with that discussion, can people identify system properties that are functions that are path independent? That could be path independent. So it doesn't matter how you go from equilibrium state 1 to 2. So let's just say we have a pressure volume diagram, and let's say this is our equilibrium state 1, this is our equilibrium state 2, and we have some crazy little path that takes us between those two states that are equilibrium states. What could be something that is, and let's say we have another path. Let's say that's the black path, and now we'll have a red path that is this way. Again, the same two equilibrium, and we'll just add one more for we'll make it blue. Blue is my favorite color, so we'll go this way. And so we have a black path, a red path, and a blue path. They start at the same point and end at the same point. So for this type of a process, for these three types of processes, we see that we're going between two equilibrium states, 1 and 2. And so if we wanted to say that regardless of how we go from 1 to 2, there would be some change in a function or a variable or a property. And so those would be path independent properties because it wouldn't matter which path you took between 1 and 2. And so does anyone want to guess at least two properties that would be fitting that description?
Heat, Q.
Sorry?
Heat, Q.
Not quite. Okay, so we're going to get to heat in a moment, and you'll see no. Surprisingly, no. And we'll see that. I'm glad you brought that up. It's a very important point.
N?
Okay, so let's say we keep N constant. Okay? Yeah, if it's a closed system in which we don't allow N, N will not change. But just looking at this graph, let's say you're going from state 1 to state 2, okay, along the red, the black, and the blue paths, what system properties don't depend on whether the change, let's say, in the system property, right? There's going to be a change because you're going from one equilibrium state to another, from 1 to 2. So there will be a change in this property, but the change should not matter. It should not depend on the path. And so
what about entropy?
Sorry?
Entropy?
Okay, we'll get to that. You are correct, but I haven't shown you that yet, but I will later on. That's correct. Entropy is?
Internal energy.
Okay, we haven't discussed internal energy yet, but that is also another thing. We will see that in a moment, I hope. But just from the graph, just from this graph, I hope everyone can see it. So yeah, entropy, we call that S, yes. Somebody said internal energy, U, these are all, yes, path independent. Anything else? Just from this plot, what?
Pressure?
Ah, good. Pressure, yes. Why is that? So I'm not keeping the tabs open. Who was this? Who was speaking? Whoever said pressure?
It was me, Khalil.
Leo. Okay. Do you want to give an explanation why? You're right.
I guess because there's no sign in pressure, like it's just a change, and the change is going to be equal from 1 to 2, no matter which direction.
Right, exactly, right? So let's say this is P1, and here we have P2 for the pressure. Does it matter? Does the change in pressure matter or depend on which path you take, red, black, or blue?
No.
No, right? Because what is the change in pressure? How would you compute delta P?
P2 minus P1.
Yeah, exactly. So delta P is P2 minus P1, regardless of whether you, so that's for the blue case. Let's go for the red case. What is delta P for the red case, for the red path?
Also P2 minus P1.
Yeah, and for the black path? It's all the same. So delta P doesn't change. It doesn't matter how you go from equilibrium state 1 to equilibrium state 2. Delta P is always going to be P2 minus P1. And so that's why it's called path. So pressure is a path independent variable, path independent function, path independent system property. Just as entropy and internal energy, as a few of you have mentioned, but I haven't introduced those to you yet, and I haven't proven to you that they are path independent. I have to prove it to you, and I will later as we get to them. Okay, but yes, pressure here, I have shown you that pressure is this thing that's path independent, right? I hope everyone can see it. Is there anyone who wishes me to be a little bit more clear on that? Okay, remember work is not path independent. Right, work is path dependent, remember? Because we saw here that depending on the path we went from 1 to 3, we obtain different values for the work. Okay. Okay. So there's a delta P. Please, is there something that's confusing people? I really want people to understand this difference between path independent and path dependent. It's very important. Okay, one other thing from the graph. So now that we know that pressure is path independent, what else can you tell me? It's so obvious, I think, from the graph.
Volume.
Ah, exactly, volume. So volume has to be in, and I can write the same types of relationships I did for delta P for delta V. Convince yourself it's going, of course, there'll be V's instead of P's, but you get the idea. Okay, any questions? So these are examples, in addition to entropy and internal energy, which we will get to later, that are path independent functions, variables, properties. Okay, you can use them interchangeably. And you'll see that S and U actually can also be called, they are system properties. They can also be called functions. And you'll see that functions essentially have an equal sign. There's an equation for them. And you'll see why S and U are functions a little later when we get a little bit more sophisticated in our discussion of thermodynamics. And all of this is important because this is how once we have functions for these properties or variables, we can compute their differences. Remember, we were interested in computing things like delta U, delta S, delta G. And so that's where we're after here, okay? And in fact, can anyone sort of fathom why having something that is independent of the path be a good thing? So why is something like delta P, which is independent of path, why is that good that it's independent of path? Why might that be a good thing?
Because functions that involve it will be easy to compute with the fundamental theorem of calculus.
Okay, very good, very sophisticated answer. Yeah, exactly. They make life easy because if all you're interested in is a delta for something, again, right? You've encountered delta G's, delta H's for reactions, delta S's perhaps, a delta P for a pressure change. If you want to calculate that, you can essentially have any process that takes a system from one equilibrium state to another and compute delta whatever that path independent function is. You don't have to worry about the path. And if you can find an easy way to compute that delta P, go for it, because that's all you want. That's all you want is the delta. Okay? And so that's right. It's a good thing to have things that are path independent. So, and it turns out, luckily for us, that a lot of these thermodynamic properties that you've been introduced to are path independent. That makes life very easy to go between equilibrium states. The other thing I want to, and I think this might be something that is not something I didn't maybe emphasize, is that work is not related to a change in the sense delta W. Okay, so if you think about it this way, it may help you distinguish path dependent versus path independent. So there's no delta W. Okay, so there is a delta P. So we'll use these guys for now because that's all I've introduced. There is a delta P and a delta V, but there's no delta W. Okay, a system can have a pressure at equilibrium. Okay, a system can have a pressure or a volume. Okay, you can have a beaker of water that's closed and it can occupy some amount of volume at a particular pressure. And so we can ascribe or relate or associate a pressure and a volume to a system at equilibrium. We can say, all right, this system is at pressure and volume. This is what we've done in these plots here. In these types of plots, we've said, right, that this equilibrium state is at P1, V1. And this one is at P2, V2, because we can identify very explicitly with a state at a system in a state at equilibrium, a pressure and a volume. So we can say a system has a pressure and a volume. We cannot say that a pressure has work. In any of our discussions so far, looking at labels for these graphs, you can go back and look at that and look at your text in the reading material. We never write for this equilibrium state 1, P1, V1, W1. We never write that. And we don't write for equilibrium state 2, P2, V2, W2. We don't do that because there is nothing, it makes no sense to say that a system has work 1 and a system has work 2. Okay? Remember, work is something that is done during an interaction between the system and the surroundings. So that work only exists during that period of interaction. Once that interaction stops, that's it. Okay? There is nothing that says, oh, this system has W1 amount of work in it, or this system has W2 amount of work in it. And this is something that's very, very important. That's why there is nothing called delta W. Okay? So depending on the path you take between two equilibrium states, W, the amount of work that is done or on the system or by the system can be different, but there is no delta W. In contrast, there is a delta P and a delta V. And I think this plot really, if you go back and just contemplate it a little bit and make sure you understand why I crossed out the W1 and the W2, you will understand a very important concept. Okay. And so again, I make sure that that's a very important concept. Any questions? I'm really belaboring things here because I want to make things very clear for everyone. And I don't mean to bore you. Okay, so I'm going to move on now. Any questions or comments, contributions? I appreciate the discussion and the feedback. Okay, so let's go on to heat now. Okay, so let's consider heat. So heat interactions. Okay, so we saw in our abstract system with surroundings that we have two types of generic interactions, work. So we already discussed work. And again, I think this figure shows a lot, pictures worth 1,000 words, that it's an interaction. And so this only exists, the work only exists during the moment or the period of interaction. And now we have heat interactions. Okay. Again, you might think already then that there must be some analogy in terms of the nature of heat with regard to the nature of work. we saw that work is path dependent. That must mean that heat is also path dependent because it only exists during this moment of interaction. The other thing is there's no such thing as delta Q. We can write differential forms of heat, meaning that during a process, you may have very, very, very small amounts, these infinitesimally small amounts of heat exchange between the surroundings and the system. But once that process is done, there's no such thing as delta Q because we can't ascribe for a system at equilibrium some amount of heat in it. There's no such thing as, oh, this beaker of water has Q amount of heat in it. The heat is something that flows during a process. So when you're heating the water, you can talk about heat that's flowing between the system and the surroundings. But once you stop that heating process and you insulate your beaker, and there's no heat exchange between the system and the surroundings, we don't talk about heat. So much like, not much like, okay, there's nothing about much here. Like work, heat interactions are path dependent. Okay, this is a very important, and I'll show you in a moment. Okay. And so for differential or infinitesimal differential exchanges of heat between system and surroundings, we write dq. Just as we wrote dw with a line to show that it's a path-dependent function, this line here indicates heat interactions are path-dependent. Okay? So that line for dq, which is this infinitesimal or differential exchange of heat between system and surroundings, so we'll have dq here, okay, just as we had dw here. Okay, that dq is something that depends on path, and we're going to consider two paths in a very quick discussion of heat interactions. Any questions, comments? Okay. So heat interactions. So one, we have constant pressure heat interaction. Okay, so we have a constant pressure heat interaction. So we can visualize this in two ways. Okay, so let's say I have this piston, again, this piston assembly. Okay. So I have this piston assembly. Here I have a gas, okay? Here is some external pressure, okay? What we can do, and let's say we apply this external pressure with a block. Okay, let's just, to make it actually very, very easy to visualize. So let's say I have some mass. So let's say here's some lead, here's iron. Let's put an iron block onto this piston head, okay? So we know now that this iron block is exerting a pressure on the gas in this direction. Okay, does everyone follow that? Okay, so that's our external pressure on the gas. And so what we're going to do, let's say these sides are insulated, and the only way that any heat, and even up here, everything is insulated. Okay, so the top is insulated. The only thing that's not insulated is this bottom part. And what we're going to do is put a little flame here. I don't know. meager, okay, so some flame, some heat source, very unsophisticated heat source. And what that's going to allow us to do is heat the system, which is our gas. This is our system, is the gas. It's going to allow us to heat the system, okay? And we say that this is a constant pressure because the iron block is always going to exert a constant pressure downwards on the gas, regardless of what this piston head is doing in terms of its motion. Okay, this piston head, as we heat the gas, what do you think would happen to this piston head if we heat the gas?
Will raise.
Right, exactly. Well, then, so the gas would be, what's the technical term here?
Doing work on the surroundings.
Yes, yes, and it would be, yes, you're right, and it's expanding, exactly. The volume is increasing as we heat it. All of those comments were correct. Right, so the gas would be expanding as we heat it. It's doing work on the surroundings, that's right. In this case, it's very obvious. It's working on that iron block. If the cylinder is going up, the gas is pushing the thing up. So it's working on this block, right? As you would, right? Pumping iron, right? It's pumping iron essentially. So the system is doing work on the surroundings. So this is constant pressure. And we know that heat is moving into the system, or heat is flowing into the system because we have a heat source that's pumping heat into the system. Okay, and so this area of the piston cylinder assembly is not insulated so that heat can go into the system. So we see we have heating here, in this case, at constant pressure. Okay, this is called constant pressure heating. And so let's consider the differential changes in heat. But first of all, we know that heat is coming into the system. And so what is the most palpable thing that's going to change besides the pressure and the volume in the system? That's a system property. When you heat something, what is it that changes? This is the first thing that pops into your mind. What system property changes?
Temperature.
Temperature, right? So now, heat is not temperature. Heat is related to temperature, okay? So we see here that if we add heat, and let's say we're talking about a differential amount, a very small amount, and we're going to call that, again, because it's path dependent, dq. And since this is constant pressure, I'm going to label this dq with a p as a subscript to indicate that this is heating. We're adding bits and bits and bits of heat, or the system and the surroundings are exchanging bits of heat, dq, at constant pressure, and that's called dqp. Okay? So that's the nomenclature. So dqp is going to be related to dt, and T here is the temperature. Somebody just said that. Again, I don't have my list of names, just so I don't have my screen cluttered, but so if I don't say your name, my apologies to everyone. Just accept that for the remainder of the course. There's no offense meant. So we see that dq is related to dt, right? This is T is equal to temperature. Okay, and so they're related, but they're not the same. Okay, and I say it again, dq, q is a path dependent function, okay, and T is not a path dependent function, because just like pressure and volume, temperature is path independent, right? You can go between equilibrium states and delta T will not depend on the path. That's one of these things that's path independent. So does anyone remember the relationship between dq and dt, or q and t? There's a relationship, in fact, and it's a equals, so it's a very strict relationship. Okay, I will remind you. And it's this thing called C sub P. And the C sub P which is a function of temperature. Okay. Does anyone remember what that is called?
Heat capacity.
Exactly. And we'll be a little bit more precise now and call it and so this is the relationship between temperature, which is a path-independent function or a path-independent property of a system, and heat, which is not a property of a system, but it is a path-independent function or a path-independent variable, if you want to call heat a variable. But it's a path-independent path-dependent function. Sorry, path-dependent. Q is path-dependent. So the specific heat is the function of temperature that relates these two beasts, Q and T. And I know you've seen this before in various forms. Okay, so in the integrated form, okay, so let me just write dQp is equal to, this is the constant pressure now case. Okay, so this is the differential form. We always start with the differential form because it's a very general case, and then we can integrate it between the limits that we're interested in, right? If we have a change in an equilibrium in a system between equilibrium states, you integrate, and that's how you can get Q. Now, if Cp of T is constant, or really, this is the way to say it, it's weakly dependent on temperature. So weakly meaning weak, as in W-E-A-K. Weakly dependent on temperature, right? We can write Cp of T as just a constant Cp. And so if this is the case, and this we will use functions of Cp that are not constant, but if it is the case, then dq at constant pressure is equal to Cp times dt. And maybe this is a way you've seen this relationship before. Q at constant pressure is equal to Cp times delta T. Maybe you've seen this form in terms of the heat capacity before, but this is the general form that we will use for this course right here. Okay, and so this is the important one. Does this ring a bell at all for people? I hope. Okay, so this is the constant pressure process for heat, and we see that at Q. And here what I want to emphasize again, there is no delta Q. Even if you've been introduced to this relationship with deltas, I urge you to sort of try to abandon that, because there is no delta Q. Deltas imply that systems at equilibrium have a property, okay? And so Q and W are not properties of a system at equilibrium. They only exist during this transient period of time when there's an interaction. Okay, so once that transient period of time that involves the interaction is over, that's it, it's gone, right? The Q, there is no Q or W, and that's why there's no delta Q. But we see here that there is a delta T. Okay, so that means then that T must be a path independent function and Q is a path dependent function. Okay, any questions? So here's another example of this relationship here, or this notion of path independence and path dependence. So that's the constant pressure case. Any questions? Any questions at all? Okay, I'm going to move on to the next case. So we've looked at the constant pressure case for heat interactions. So the only other one that we're going to consider here is constant volume. Constant volume heat interaction. Okay, and so again, we can have our piston assembly. Okay. And here we have our gas, which is our system. Okay. We can have insulated everything except for the bottom. Okay. But this time, we're going to have some stoppers, let's say right here. So what this does is prevent any motion, for lack of a better word, I don't know, we'll call it stopper. Okay. And what this does is prevents motion of piston head. Okay, so this piston head is going to remain wherever it is. Okay, because of these stoppers, it's going to prevent it from moving up. Okay, and so we're going to start initially at some equilibrium state where this piston has achieved its equilibrium height or equilibrium position. That means that the gas has equilibrated in terms of its temperature, pressure, and volume. So we've let everything come to equilibrium. That piston head finds its position that it's comfortable with. Well, really, it's the equilibrium pressure of the gas. Okay? And then we just stop it there. We put these stoppers there so that the thing can no longer move up. Okay? At least it's going to be not moving up. Okay? Now what we're going to do is the same thing. We bring in our little heat source. Okay, so this is our heat source. Okay, and we're going to heat the gas. But this time, okay, there's going to be no change in volume because that piston head is not going to be allowed to go up. We've stopped it. And since we're heating the gas, we know that gases want to expand when you heat them. Okay, so there's no way that the piston is going to go down. Okay, if we're going to add heat to the system, it's just impossible. Okay, the only way that piston head could go is up, but we're going to prevent it from going up. So this is constant volume addition of heat, or this is a constant volume interaction that involves heat between the system and the surroundings. And much as we did with the case of constant pressure, we can write expressions for the differential heat exchange between our system, the gas, and the surroundings, in this case, the heat source. Okay? And so dq, again, we had that line to represent that q is a path-dependent function. And now what would be the subscript for q in this case?
V.
V, yeah, exactly. That would represent constant volume. So you see here now already we have path dependence. Up here we had QP, Q sub P, to represent a path that is at constant pressure. Okay. Now we have a path that is at constant volume. So this is path dependence. Okay. And we know again that if we add heat to a system, the most palpable thing that's going to change as a result of heating is temperature, right? So there must be a T or a DT, a differential change in the temperature that's associated with this differential or this very small amount of heat that we add to the system, in this case, our gas at constant volume. Okay, we don't allow the volume to change. Does anyone remember the relationship here? Okay, I will remind you. And that is the same thing as we had. It's analogous to what we have for constant pressure, but now what we have is C sub V as a function of temperature, not C sub P. And C sub V is the constant volume heat capacity. Okay, so there's a different heat capacity whether you heat something at constant volume or whether you heat something at constant pressure. And the difference is the heat capacity, one is a constant volume heat capacity, the other one is a constant pressure, and they are both functions in the very general sense of temperature. Okay, you may have been introduced to problems in the past where you've been told assume that it's constant, or maybe you were not told that it's a function of pressure, CV and CP, but in the most general sense, and since this is upper level course now, we can appreciate that these guys are temperature dependent. Okay, to first order, the first effect is temperature dependence. Okay, there may be minor effects of pressure and other things, but the most influential effect comes from temperature. That's why they're labeled as functions of temperature. And so we have dQV is equal to CV of T dt. This is the differential form, right? If we assume CV of T is weakly dependent, temperature dependent, that means it depends very weakly on temperatures, enough so that we don't have to worry about its temperature dependence. Then we can take CV equals a constant, independent of temperature, and so then dQV is CV dt. And then we know that if we integrate, QV then becomes CV delta T, okay? So this is only if we take CV to be independent of temperature, but this is the most general form, and this is the form to use for this course. But this is an example of how one might be able to simplify a problem by being told or by being able to make the approximation that CV is weakly dependent on temperature. So that's the point I'm trying to make there, okay? So we can actually start here, which is the most general form, and perhaps simplify to these two if we are able to make this assumption. Okay? Any questions on that? Any comments or any need for clarification? So we see here then, to recap, I'm running out of time, so I will recap here or have takeaways. We have dQ, which is a heat interaction. This is path dependent. It's a path dependent function. Okay. It's only, I don't know how else to say it. I'm just going to say it only exists during an interaction between system and surroundings. Between system and surroundings, okay? A system does not have Q amount of work, a system at equilibrium, okay? We don't say that. As opposed to we saying a system is at temperature T1, or a system has temperature T, okay? Or it has internal energy U, as someone has said, but I haven't told you what energy is yet. And since it's a path dependent, there's two types we've discussed, and this is the form that we're going to use. That's why I'll keep them in these forms. dQ at constant pressure is the constant pressure heat capacity dt. And the other one is at constant volume, and that's the constant volume heat capacity, which is a function of temperature times dt. Okay, so these are important as well. Okay. So that's it. There you have it. So far, we are set up now for the first law. We have dW is equal to minus P external dV, and dQ at constant pressure is equal to Cp of T dt, and dQ of V is equal to Cv of T dt. Okay, so these are the major conclusions that are now going to allow us to move forward and consider, oh, right, and these are all path dependent. Okay, so now we're ready to look at the first law as we continue this week. So, any questions, any comments? I'm going to end my discussion today at this point. We'll do the first law next class. So I will leave this up open for questions, comments, contributions at this point. No? Okay. All All right then, I'm glad everyone made it, and I really was happy with the discussion today. A lot of contribution and feedback. I will take a little break. I have office hours, I guess, starting at 11:10, so I'll let you take a break if you need, and I'll be here. I wish you all a great week and a happy week and a safe week. And I appreciate your attention. All right, so I'm going to end the lecture for today.
Thank you.
Okay. Thank you.